a product within the integral in such a way that one of the factors is not in any way, shape, or form the derivative of the other factor, then integration by parts might be an appropriate approach. Okay? So we have x and we have e to the x. I can't use reverse power rule. I can't just take the e to the x as my antiderivative. That's not going to fly. Whenever we have an e in our integral, whatever the power is usually our u if we're using u substitution. But the derivative of u would not be to the x. I wouldn't be able to cancel that out. So those strategies are all out the window. I can't do anything with that. But what I can do is integrate by parts. So I'm going to let u and dv be equal to some expressions. They're little tips there. They're your classic textbook tips, which means that they're understandable to some but not all. When you define your u, it has to be something that you can take the derivative of. When you define your dv, it has to be something that you can find the antiderivative of. All right? If you can't find the antiderivative of whatever you call dv, then you chose the wrong dv. Because the whole point of this thing is to be able to take the antiderivative of something you didn't already know the antiderivative of. Okay? So if I go, let's say for example, I'm like, okay, I'm gonna design this, and I'm gonna let my u be equal to 1, and my dv be equal to x e to the x dx. I haven't made the situation better. I've not improved anything. So why would I do that? All right? What you want to do, again, is looking at your factors, and we have 3 of them here. All right? We have an x, an e to the x, and we have one more, the one that's hidden in plain sight, a dx. All right? Because that whole Riemann sum activity, the tech assignment that we did, that was really to establish the point of the importance of the dx. That dx is a factor. It is a multiplier that's contained within your integral. So these 3 factors have to be accounted for. Some are going to go with u, and some are going to go with dv. I need factors, a factor or factors from these 3 that I can take the derivative of. Right? I look at x and I say, yes, I can certainly do that. Come right here. The dx, I'm not taking the derivative of dx, so that should go with the dv. All right, that's always going to be the case. You can sort of rely on that. I mean, it's already part of the derivative notation. What purpose would it serve to take the derivative again? The only thing that's left would be my e to the x. Now, e to the x is one of those kind of two-way sort of functions. You can take the derivative of it, but you can also take the antiderivative of it very easily. The derivative of e to the x is e to the x. I could have called u e to the x if I'm just saying, let the thing that I take the derivative of e to the x. I could have done that. But then I would have had to let x be my dv, and while I can't take the antiderivative of that, it doesn't make things better. I went from something that was a power of 1 to something that's power of 2. That's going to complicate things. It's not going to simplify things. This is the best arrangement to simplify things. When I take the derivative of this in a second, it's going to go to 1. When I take the antiderivative of this, it's not going to change. So if anything, it's going to get easier. Worst case scenario, the level of difficulty doesn't change at all. All right? So after we designate our values, we take the derivative of whatever we call u, so du dx, but we could also do it in pretty much the same way we did with u substitution, which is to skip this step basically and just go right to du equals 1 dx or just dx. All right, because that's going to have to happen anyway. Then we're going blue here, take the antiderivative of both sides. So antiderivative of 1 dv is just v. Antiderivative of e to the x is e to the x. Technically e to the x plus c, because it's an indefinite integral, but I'm not done with the process. I'm going to just just pop a plus c on at the very end. Okay? I don't want to have to do an intermediate steps and then have to worry about that along the way too. Right? So I have all this information now, and it's good information. We apply the rule. U dv, the integral of u dv, so here's my u, here's my dv, is equal to uv minus the integral of dv. So let's set that up. So this is my u dv. That's going to be equal to, so that's just the original problem. uv, my u is x. My v, just kind of hunt around for what you need. My v is e to the x minus the integral of the v again du. And fortunately, in this case, doesn't always happen, can't guarantee it, but in this case, du happens to be dx. So now I'm just one small step away from the final answer. Right? So I have x, e to the x, minus the antiderivative of e to the x is e to the x. Then I pop on the plus c. Yeah, because it would have been a pain in the ass to put it in over here. Yeah. It would have made a mess. We didn't want to deal with it. We got constants everywhere, so not working. Save it for the end. The big challenge when it comes to integration by parts is twofold. One, determining what your u and your dv should be. But that's actually the second of the two challenges. The first challenge is determining whether an integration problem is best solved with integration by parts. Like if I give you a question on a test, you look at it, the big concern is not going to be how do I do calculus. It's more so going to be, crap, is this u substitution? Is it a trig substitution? Those are usually pretty obvious. You never know. Is it integration by parts? Is it partial fractions? What method do I, is it a rule that I should know? That paralysis by analysis, that 3 minutes where you're staring at the problem, trying to figure out what method to use before you put pen to paper, that's the killer. What you need to do is just say, this is what I think it is, and just start doing it. And then if it turns out that you're going down the wrong path, make sure you have scrap. Because you just take it right from the beginning. Don't try to erase your work. Don't try to find your mistake. Just say, oh, that wasn't integration by parts. Let's try something else. All right? In most cases, that's pretty much how it's going to play out. All right? Now, number 2, it's got a natural log in it. Now, you might look at that and say, well, that's really easy to take the derivative of. So let's try that. It does. That's why I chose this arrangement. Because we're about to pay a hefty price. All right. There's a lesson in here. So you look at the x squared, say I can take the antiderivative of that. You take the ln of x, say I can take the derivative of that. Should be mere child's play. Du would be equal to ln of x is 1 over x dx. Antiderivative here, v would be equal to 1/3 x cubed. And again, we hold off on adding the c until the very last step. Right? It ends up coming out in the wash. It's not going to make it. It's going to work out to be just a plus C at the end, no matter which method you use. So why not do the simpler way? All right. So we have our U's, we have our V's, we have everything. All right. So UV no, actually, at this moment, I think it turns out that this was the correct substitution. So, hold on, let me just, I think I might have been thinking of a different problem. It might be number 3. So anyway, UV, well, I wrote VU, but it means the same thing, minus the integral of V du. So 1/3 that's the V du. Yeah, I was thinking of a different problem. Oh, you know what I was thinking of? I was thinking of the integral of ln of x, which I must have changed the question. No, no. The 1/3, the one in green, yeah, that's the UV part of it. Yeah. So I'm going to have 1/3 x cubed ln x minus 1/3 x squared dx. Oh, this red looks out of place. And so, reverse power rule gets you where you need to go, and then that's all there is to it. I swear this is... I must have changed the problem. That's so weird. Okay, well, whatever. So then you get to number 3. Number 3 is the interesting one, because it doesn't look like it fits in this topic at all. But you know, we just talked about inverse trig functions, so you figure, well, it had to come in somewhere. You know, so here's some trig, here's some inverse trig. You see the bounds of 0 to 2. That's your license, if you wanted to put this right in your calculator and call it a day. So on a test, never lose sight of that. If you have boundaries of integration, you don't need to do it by hand unless I tell you to do it by hand, and I don't remember any instance on any tests from here on out where I tell you to do any definite integrals by hand. So, you know, you should be in pretty good shape there. That being said, what if I gave you this problem without the bounds? Oh my God, it kills me every time I see it. So let us investigate. Now, if you can identify this as integration by parts, then you've pretty much already solved the problem. Because everything has to work out in a particular way in order for it to work at all. All right? When you're choosing what's going to be your U and your dV, well, fun fact, you only have 2 choices. That one and that one. Right? And we already know that anything that's got a D belongs together. Right? So what does that leave? It leaves arc sine for u. But also, common sense. I'm doing this problem because I don't know the antiderivative of arc sine. So why the hell would I put it in the part that requires me to find its antiderivative? I put it in the part where I can find its derivative and work off of the rest for the antiderivative. So the arc sine goes right here. So then I'm going to take my derivative. Du equals, well, we just learned it. So obviously you would have it committed to memory by now. 1 over 1 minus x squared dx. All right, so in our general rule from 2 pages ago, x takes the place of u, and the derivative of x is 1, so that's what the arc sine of u's derivative would be. The antiderivative, well, that doesn't require any work whatsoever. I feel like I'm walking around more frequently today just so it makes my cape flutter in the non-breeze. So v equals x. I still don't know why that air processing unit, I thought it was an air conditioner at one point, but it's been running all year, and it doesn't seem to do anything except for produce like stifling heat. And noise. The noise is the issue. More. I think it's supposed to be. But earlier in the year, I don't think it's sufficiently warm or cooled this room off. And, yeah. I feel like this is the exhaust for the air conditioners in every other room. So I'm going to leave off the bounds. Arc sine of x dx is equal to uv. So uv. Now, for the amount of times we actually will make whatever v is the coefficient of u, you might actually just want to rewrite the formula and make it vu minus the integral of v du. It's just, it happens so frequently that you might just say, forget you textbook, this is the one I'm going with. And you know what? Mnemonic-wise, it's actually, it actually has a little bit more consistency. Got our V's and U's in the same order. Yeah, it might be something to it. I don't know. Anyway, UV, aka VU, X arc sine, arc sine of X minus the integral of V du. All right, they're not all going to be easy. You might, I mean, that was a weird thing to say. They might, I mean, none of them might be easy. But some will be easier than others. When we got to the integral step, the part where we actually had to find a real antiderivative in number 1 and even number 2, it was pretty easy to do. Just reverse power produces an exponential relation. Here we have to do more work. All right, so the work would be some other method of integration. So I'd look at this and say, okay, well, time to diagnose again. What method would I consider using here? U sub. And that's because if I designate the meaty part of the integral as u, its derivative would just be a multiplier of the other part of the integral. So negative 2x dx. Clean it up a little bit. Well, as it turns out, just based on the nature of the situation here, I have a negative coefficient, an x, and a dx. So I actually probably want to hang on to the negative sign here. Just get rid of the 2. So negative x dx is equal to 1/2 du. So, you get my Zark sign in here. Minus would become a plus. It's really a coefficient of 1/2, so plus 1/2. The integral will end with a du. And it's going to be 1 over the square root of u. I'm just going to rewrite the whole thing, even though I'm only making a minor adjustment. Whoa. Took off on me. Alright, so then it becomes reverse power rule, finally. So, new exponent 1/2, so we're looking at 2u to the 1/2. Multiplied by the 1/2 that's already there. Zark sign. And I could put it back in terms of x. And we would get Zark sign of x plus, let's do guys a cancel. The u, which is 1 minus x squared to the 1/2, or you could write it as a radical, plus c. What the hell? Look at that. Alright, again, this part here, from here on down, that's not the integration by parts part. That's all the u stuff that we've been doing all semester. Alright, so, you know, like sometimes paying lip service to it, but it's been there the whole time. It's the u v minus the integral of v du part of it. That's the new stuff. All right, so this is just perseverance. I mean, it takes a lot of writing, and more so because I showed every single tiny little detail here. But I mean, generally speaking, you're going to have to write probably more every time you have to define a u and substitute. But in this case, you look at it, it's got multiple levels. We had to define a u once to mean one thing, and then later on to mean something completely different. All right, so it's pretty interesting. All right, I'm just going to do this down here. So this one, also a good one. I mean, anything that involves trig. I mean, you already get a sense now that not only do I think it's important, but I also like it. And maybe that's not music to your ears, but trig is, I think, the most beautiful aspect of math. And it works its way into all corners. Sometimes in shocking ways. To think that you could be in a probability and statistics class and still have to worry about trigonometry is very surprising, but it's in there too. You know, it's everywhere. And the relationships, and I'll tell you, I don't even think I fully understood this when I was a student. The concept that you can express an algebraic expression in terms of trigonometry. Like, how would that even work, you know? But this is how it works. And really, if you think of anything as being circular in nature, then it opens a lot of pathways. And when you start talking about like a line being an illusion, that a line isn't really a line is just a subset of a infinitely large circle. It's like, well now, you know, it changes the way you think about everything. You know, so what are we drawing as a line? We're just drawing the tiniest segment on a circle of infinite size. That's just crazy stuff. And if you redefine anything that's linear in that regard, now all of a sudden you've made the basis of the entire universe circular or trigonometric. I mean, that's some pretty cool stuff. That's so inspirational. I mean, obviously something bad in what it's saying.
I'm sitting here working my brain trying to just grasp that.
That infinitely large circle, that's... Yeah. It's just... integration by parts. That's the way we're going. All right, so we have to define our U. And we have to define our dV. Okay, so I gave you two things I like about trig. There's one thing that I don't always like about trig, and that sometimes it can be ambiguous. Where it's like, oh, try this because it could work sometimes, but only on Tuesdays. You know?
We ignored the bounds, right?
Oh, I forgot about that.
I thought we just did the problem pretending that it wasn't there.
Yeah, let's just do that. Yeah. I just forgot. Yeah, so pretend there's no plus C, put a 0 to 2 and plug it in and get some numbers and then check it on your calculator. But if it's on a test, just do it on the calculator. So here we have a little bit of an issue because sine is just as easy to take the derivative of as it is to take its antiderivative. So that sucks. X squared, you can take its derivative or antiderivative with equal ease, I think. It's the same rule, just in reverse order. So what do? If you take the antiderivative or the derivative of sine, you will get a function that's no more or no less complicated than the original one. Sine and cosine are the same function, just one is shifted over. All right, so it doesn't change the level of difficulty. If I take the antiderivative of x squared, it will increase the difficulty because it's increasing the power. If I take the derivative, it will decrease the difficulty because it's decreasing the power. So it's a thought, it's an idea. This one, it wouldn't matter where I put it, but this one makes life easier if it goes here. I kind of pick on my teachers a lot because I say things like, oh, I kind of wish somebody told me that when I was learning this stuff, because my teacher said things like, oh, just pick a U and a dV and just see if it works. More likely than not, I was just not paying attention when they were giving a really detailed explanation of the Y, and I just missed all of that. There was no phones then, but I still found other ways to occupy my brain than to be paying attention in a class that I thought I was smarter than the teacher in. So, which also was a big issue for me. Anyway, derivative, du equals 2x dx. And it was very rarely true, by the way. Antiderivative. V equals negative cosine x. So, perseverance is the name of the game. I have the integral x squared sine x dx. UV, so purple. Say it again. The derivative of sine x is cosine x, yeah. But this time we're looking for the antiderivative. Am I wrong? No, I think I'm right. Yeah. So UV, so negative x squared cosine x minus the integral of v du. So that's going to be negative cosine x, and then du is a little bit more elaborate than it's been, times 2x dx. So a little bit of housekeeping. And then belief. Belief that you didn't make a mistake early on and choose the wrong u and v, right? And this is the kind of problem that makes things interesting, because you get to this step and you say, well, I can't find the antiderivative of that either. That's screwed up. Must be the other way around. Then you erase that, go through that process with the other u and the other possible RDB, get to this moment here, get stuck again. Now it's a crapshoot. I don't know which way to direct. If you have a little bit of perseverance and continue on from here, you'll get there. It's just a little bit of a ride for this problem. So let's take a look at this bad boy right here. Right? And I know personally that there's potential for this to be the correct approach, because the power in my new integral, even though it's not anti-differentiable the way I have it, just like the first one wasn't, it's a step in the right direction. The first one was a power of 2, this is a power of 1. Hey, maybe if I do it one more time, it'll be a power of 0 for the x, meaning the x will go away, and then I can take the antiderivative. If you assume that trend continues, and there's no reason to assume that it won't, then we could be in a pretty good spot here in a minute. All right, so we would have x and then cosine x dx du equals dx, v equals sine x. So this is going to become uv minus the integral of v, which is sine x, du, which is dx. All right. So I'm going to work this to its logical conclusion, and then I'll bring it back into the fold with the other thing. But now I know we're in the home stretch, because I can find the antiderivative of sine x. We've already done it in this problem. So we have x sine x. That's going to be minus a negative cosine x, so really plus cosine x. All right. Now I'm going to bring down the other stuff. Negative x squared cosine x plus 2 times all of this stuff plus c. Debatable whether or not it's worth it to distribute the 2. Debate's over. It's not worth it. Yeah, I just did it in just real quickly. Once you distribute the 2, there's no like terms. Maybe you have a common factor, but it's not going to advance the plot, so we would just leave it here. What was this, 41?